Okay, so we are continuing section 4.6. Section 4.6 deals with rank. Rank is the dimension of the column space of a matrix A. But there's an interesting result that relates the rank of the column, the rank of a matrix A. Again, rank by definition is the dimension of the column space of A. But by theorem 14, okay, which we touched upon in the last class, theorem 14 says that if you, well, first of all, the dimensions of the column space and the row space are equal, but also the rank of A, which is the dimension of the column space of A, and the dimension of the null space of A, the sum of that will equal the number of columns in the matrix. Okay, so, and we looked at an example in the book, but I want to give you just another little example here that I made up that can kind of help you see this, as well as a few other things we talked about. So let's see here. Let me go on 3-point font here. All right. So let's say that you had a matrix A. Okay, and this matrix A has columns 1, 0, 0, 2, 1, negative 2, 3, 0, 0, and 4, 0, 0. And we want to reduce, we want to determine what the dimension of the column space of A is and what the dimension of the null space of A is. Okay, so we can get the matrix in echelon form. And so naturally, I'm going to take 2 times the second row, add it to the third row, and replace the third row with the result. And if we do that, this is what we're going to get. And I can even go a little further than this. I mean, I can also get this matrix in reduced echelon form. I don't have to, but I'm just going to do it for the purposes of this example. And so that means the 2 here, I would want it to be a 0. So I take negative 2 times the second row, add it to the first row, put the result in the first row. Okay, so and let's call this B, matrix B. Okay, so based on this, what's the basis for the column space of A? What vectors form the basis for the column space of A? Well, where do we look to determine that? Sometimes you can see it right in the matrix A, but here we want to train ourselves to look at the matrix B, okay, to figure out what the basis is. So in matrix B, and because matrix B is in echelon form or reduced echelon form, so it's easy to tell us what the pivot columns are. That's right, Mikhail. And so what are the pivot columns? Which columns are pivot columns? Matrix B here. What are the pivot columns? Is it the first and third column, the second and third column? That's right, Bella. That's right, Marcella. Very good. It's going to be the first column. Maybe I'll just check that, and the second column. Okay. So that means then, though, the basis for the column space of A, we would go back to the first and second column of the original matrix A to determine the column space, or a basis for the column space. And what's the rank? What's the rank of the matrix A? The rank of the matrix A, remember, is the dimension of the column space of A. What's the rank equal to? How many vectors are in the basis? 2. That's right, Melvin. The dimension of the column space of A is the number of vectors in the basis for the column space of A. And we have these 2 here. Okay, now what would we haven't found the null space, but what would the dimension for the null space of A equal? That's right. Good, Bella. It would equal 2. Because by the rank theorem, the dimension of the column space and the dimension of the null space has to equal the number of columns in the matrix A. And since this is a 3 by 4 matrix A, 2 plus only 2 equals 4. So we didn't find the basis for the null space of A, but we know the basis will consist of 2 vectors that are in R4. Are there any questions so far? All right, let's move on. We also want to talk about the basis for the row space of A. So the row space of A, now what we do is that matrix B, we look at the row vectors. How many row vectors are, what row vectors then form the basis? What row vectors form the basis? Well, how many do there have to be in the basis for the row space of A? How many vectors do there have to be? That's right, Nikhil, 2. And the rank theorem says that the dimension of the row space is the same as the dimension of the column space of the matrix A. So 1, 0, 3, 4 is one of the vectors in the basis for the row space of A, and the other vector is 0, 1, 0, 0. Now, could we also have as a basis for the row space of A, okay, could we also have this answer? Could we go back to the original, well, I probably want to put that in green. Can we go back to the original matrix and pick out the first 2 rows? In other words, 1, 2, 3, 4, and 0, 1, 0, 0. Is that also a basis for the row space of A? It is. So this answer is good, and so is this answer. Now the column space of A, you always have to go back to the original matrix to pull out the columns that correspond to the pivot columns. But for the row space of A, yes, you can do that, but you can also work with the rows of the reduced, of the echelon form of the matrix A or reduced echelon form of the matrix A. Now, I'll ask you this. If this is the case, does the span of the vectors 1, 0, 3, 4 and 0, 1, 0, 0, does that span have to equal the span of the vectors 1, 2, 3, 4 and 0, 1, 0, 0? Are their spans the same? Absolutely. That's right. That's right, Mikhail. They are. Because they're both bases for the row space of A. So the space spanned by those vectors has to be equivalent. They're both bases for this subspace, this row space of A. So the span of the vectors has to be the same. But you might say, well, Dr. Diddy, if I look at the 1, 2, 3, 4 here, okay, how am I going to get that based on the span of the vectors 1, 0, 3, 4 and 0, 1, 1, 0? That's no problem. No problem. Just take 1 times the vector 1, 0, 3, 4 and add what times the vector 0, 1, 0, 0? What number? So the vector 1, 2, 3, 4 equals 1 times 1, 0, 3, 4 plus what number times 0, 1, 0, 0? What's going to have to go here? One, two, three, four. What I'm trying to say is this. The span of both of these bases, since both of these bases here, both of the bases are bases for the row space of A. That means, and the row space of A is a subspace of A. The bases have to span the same space. So what I'm saying is, okay, well, the second choice for the basis, okay, has as one of its basis vectors 1, 2, 3, 4. Can that vector 1, 2, 3, 4, is it equivalent to some linear combination of the basis vectors 1, 0, 3, 4 and 0, 1, 0, 0? So here's what I'm asking. 1, 2, 3, 4 equals 1 times 1, 0, 3, 4 plus what number times 0, 1, 0, 0? What's going to go here? What's going to go here? What number? Well, what's the only difference? What's the only difference? What's the only difference between I really don't want to give you the answer. I want to see if somebody could offer a guess here, a good guess. Well, go ahead and tell us, Mikhail. That's right. Good. Thank you. It's going to be 2. It's going to be 2. Right? It has to be. Because then if you take 1 times this vector 1, 0, 3, 4 plus 2 times the vector 0, 1, 0, 0, you're going to get the vector 1, 2, 3, 4. And we're writing the vectors in coordinate notation. But what I'm trying to point out to you is, for some students, it seems sort of odd that the row space of the reduced form of the matrix A is equivalent to the row space of the original matrix A. But it's true, and this is just a little example to just sort of help you feel comfortable with it. Okay, are there any questions on that? The row operations preserve the row space. The row operations do not preserve the column space, though. That's why when you identify the pivot columns of the matrix A, of the reduced form of the matrix A, whether it's echelon form or reduced echelon form, when you identify the pivot columns, you have to go back for the column space of A and find the corresponding columns to the pivot columns in the original matrix A. Okay? But you don't have to do that for the row space, and this is just a little kind of discussional problem, so you can see that. Was this helpful, class? This little example? I know Mikhail likes it. All right, Marcella likes it. Good. All right. And David, wonderful. All right, good, good. All right. So I think it helps a lot in linear algebra to have sort of nice little examples. Okay, all right. I want to do a few more problems here from section 4.6. Are there any questions before we move forward here? Okay. Okay, let us see here. Okay. Let me give you a moment to copy this example down. All right, and I appreciate all responses. All right, so David thinks he's not sure, but he's thinking no. Mikhail's sort of on the fence here. He thinks no now. Okay. All right. Well, let's see here. So this is one of these conceptual type problems, but let's remember what this section's about. Rank. So remember, by the rank theorem, the rank of A plus, which is just the, again, that's the dimension of the column space of A. Okay, the rank of A plus the dimension of the null space of A is going to equal n. Okay, so here we're saying that, well, could this 6 by 9 matrix have a two-dimensional null space? So n in this case is 9. The dimension of the null space is 2. That means the dimension of the column space would be 7, right? So effectively, what you're saying here, you know, well, what you're saying is that if this 6 by 9 matrix, okay, had a two-dimensional null space, then hold on here, let me just make this a little cleaner. That means the dimension of the column space of A would be 7. But could the dimension of the column space of A, could it be 7? In other words, could a basis for the column space of A consist of 7 vectors? 7 linearly independent vectors. Mikhail, why don't you think so? Mikhail says no. David said no. That's correct. Mikhail says there aren't enough pivot columns. Yeah, I'll tell you what, that's right. Let me show you the solution. But Mikhail, and I assume David's thinking the same thing. You're on the right, you're right. Okay, so this is now like something you would see in my math lab homework for like maybe multiple choice kind of problem, right? So the answer is no. Answer is no. Let me give you a moment to copy this down, and then we'll talk about it, okay? Okay, so let's take a look at what we have. So let's say you had a 6 by 9 matrix, okay, and let me just get this font down a little bit. Okay, and just for all intents and purposes, I'm going to call the 6 by 9 matrix matrix B. So I'm used to calling my matrix matrix A, but matrix B would be like matrix A in echelon form or reduced echelon form. And if it has a two-dimensional null space, then the rank of B is 7 by the rank theorem. But the column vectors in this matrix B would have to be in 6-dimensional space, R6, because you have the matrix is a 6 by 9 matrix. So the number of rows is 6, right? The number of rows is 6. Let me just highlight that a little better. Yeah, the number of rows is 6.
So that means there can only be 6 entries in the column vectors of B. And so the most you could have, okay, the dimension of the column space of B cannot exceed 6. Cannot exceed 6. Because the vectors, the column vectors in the matrix B, live in 6-dimensional space. And the largest number of vectors that you can have, well, I want to say this right. Now hold on. Yeah, the column space of B, for instance, could consist of 6 vectors, right? The column space of the matrix B could consist of 6 vectors. It could consist of 1 vector, 2 vector, 3 vector, 4 vectors, 5 vectors, or 6 vectors. But 6 vectors would be the most. You can't have 7 vectors, because if you had 7 vectors, you would have linear dependence, because 7 vectors is 1 vector more than the dimension of I'm sorry, 6-dimensional space. 6-dimensional space. If you were to have a basis that spanned all of 6-dimensional space, you would have 6 vectors. But if you had 7 vectors, you wouldn't have a basis, because that's too many vectors. Hence, you'd have linear dependence. So 6 vectors is the most you can do, and so the rank of B cannot exceed 6. So you can't have 7 vectors. You can't have the dimension of the column space of B equals 7. Does that help? Does that help? Help you see it a little bit? Are there any questions on that? Any questions before we move on? Mikhail's good. Cameron's good. All right. All right, let's move on then. Let's move on. Okay, another question. So I'm thinking about your homework, these conceptual multiple choice type questions. You don't want to get them wrong, right? So you have to answer them carefully, because you don't get like unlimited number of tries on those. Let me give you a moment to copy this example down. Okay, now this problem says, right, well, yeah, let's see here. Is it possible for a non-homogeneous system? So a non-homogeneous system, well, this non-homogeneous system has 7 equations and 6 unknowns. And so what that looks like is, if we were to, just sort of, I mean, it helps to write things down, but here's a non-homogeneous system, for instance. A times x equals b, where the vector b is not equal to the 0 vector. Okay.
Now, if there are 7 equations and 6 unknowns, what are the dimensions of what are the, I want to be careful how I use that word now. What are the number of rows and columns for the matrix A? If this, you know, the system of equations is represented by a matrix equation. So how many rows, how many columns for the matrix A? I'll say one thing. Since we have 6 knowns, the vector x, right, has to be a 6 by 1, right? That has to be a 6 by 1 matrix. So what would the matrix A have to be? What would its rows and columns be? Well, in order for the multiplication to be defined, you'd have to have 6 columns in matrix A, but how many rows? Now, how many rows would you need? I hate to give the answer away. Every row represents what? Every row represents an equation, right? Well, if you think about the augmented matrix for A times X equals B, every row represents an equation. So if you need 7 equations, you're going to need how many rows? Come on, somebody give the answer. Don't be afraid. Right. Belen, what do you think? How many rows would you need here? Or David? Or Cameron? Okay, good. And you guys were probably thinking the same thing. Very good. 7 rows. 7 rows. And then B would be a 7 by 1, naturally. Okay, so, well, again, we have to think about our rank theorem. We have to think about our rank theorem. Okay, so A has at most how many pivot columns or pivot positions? A is a 7 by 6 matrix. So at most, how many pivot positions would be in the matrix A? Or how many pivot columns at most would be in the matrix A? That's right, David. Excellent. 6. 6. So the dimension or the rank of A, okay, the rank of A, sorry, one moment, class. Oh, hey, Alan, I'm teaching. Can I call you back later? I am, sure. Oh, okay. All right, thanks. Okay, bye-bye. All right, class. Thank you. All right, so I gave my brother my schedule. I texted it to him, but you know, he might not look at it every time. But here we go. So the rank of A, which is the dimension of the column space of A, Okay, I'm sorry, I'm not saying this right. No, no, no. That's right. Hold on, hold on. Yeah, the rank of A would have to be, that's right, Cameron, less than or equal to 6. Less than or equal to 6. Because A at most would have 6 pivot positions, at most. But it can be less than that. So the rank of A is less than or equal to 6. Okay, so if we were to take advantage, make use of this, the answer to this question is going to be yes. It is possible for a non-homogeneous system, this non-homogeneous system, to have 7 equations and 6 unknowns. Let me show you why. Whoops, hold on, I don't want that yet. All right, so we established that the rank of A, the dimension of the column space of A, is less than or equal to 6. But by the rank theorem, well, what does the rank theorem say? The rank theorem says that, again, the rank of A plus the dimension of the null space of A equals n. So the dimension of the null, so that means then that the dimension of the null space of A would equal n minus the rank of A. So the dimension of the null space of A in this case would equal 6 minus the rank of A. Okay, and that's going to be greater than or equal to 0. If the dimension of the null space of A were just the 0 vector, its dimension would equal 0. Well, it turns out if the dimension of the null space of A were equal to 0, that's allowable, right? That's allowable. Okay. If the dimension of the null space of A were equal to 0, then there's AX equals B, that non-homogeneous system has no free variables. And so the solution would have to be unique, the solution to the non-homogeneous equation. I'm here. Question? Yep. Are there any questions? The fact that you're allowed to have 6 pivot positions in the matrix A allows you then to say that the dimension of the null space of A could equal 0. Doesn't have to, but it could. And the fact that if it did equal 0, then you'd have no free variables. Okay, and so the solution to AX equals B, if exists, would have to be unique. Okay, are there any questions on that? I mean, think about it. The null space of A, how many remember in the homeworks when you find like the null space of A, the basis for the null space of A, the null space, you can write the null space of A as a linear combination of the basis vectors, and the coefficients, the weights are the free variables, right? So now an example of this would be I'm just trying to think if I want to make sure of one thing here. I want to make sure of one thing. Let me just go to the whiteboard real quick. Hold on. One moment. One moment. Yeah, that's absolutely right. Absolutely right. If you have, but I want to say this the right way. I want to say this the right way so you can see this. So like, just take it as a little separate example. Okay. If you have AX equals B, okay, just a little separate example. And that were like this, 1, 2, 3. I'm writing an augmented matrix. Okay. Are there free variables? Are there free variables in if we solve for x? Okay. Does x have, in this case, free variables? Absolutely it does. Because you have three variables and two meaningful equations. So the answer is yes. Okay. Well, now if you were to, I want to say this the right way. If you were to, let's just say this the right way here. If you were to solve, the system AX equals 0, okay, you would have the same coefficients on the left, but then you would have zeros on the right. But the point is, the free variables that, hold on here, I'm just trying to make sure I have this proper. The free variables that show up for the non-homogeneous matrix will show up. The free variables that show up in the solution of the non-homogeneous system of equations will show up for the homogeneous system of equations, right? They'll show up, same ones. So if the dimension of the null space of A is 0, there's no free variables, and that means in the any non-homogeneous system of equation will well, I want to be careful. Yeah, the non-homogeneous system of equations will also have no free variables. And so you end, like an example of this would be something like this. So like this situation here. Here's an example. Okay, and I just made up an easy example, right? An easy example. A is already in reduced echelon form, but you can see the matrix A is a 7 by 6 matrix. Here it is, 7 by 6 matrix, 7 rows, 6 columns. And then you have the vector B here on the right with just some constants. Okay, and this is a consistent system. It's consistent. And here, the dimension of the column space of A equals 6, and you have a solution. No free variables, and you have a unique solution. So that's an example that to sort of drive it home what they're getting at here. I always like to think of examples to help me. I love examples. And sometimes I make up my own examples to help me feel comfortable with material. It worked in college and it works now, right? A lot of this material, I mean, the material can be a little bit, it can be conceptual, right? It is conceptual, but when you have an example that supports the concept, I think it's helpful. How many find this helpful, this example? It's like it's a supporting example of a non-homogeneous system of 7 equations and 6 unknowns that does have a unique solution. All right, excellent. Mikhail likes that. Cameron likes that. Because kind of when you answer these questions, you kind of like to see, okay, let's see an example of it, and well, Mikhail has a good point. By coming up with the example, it can tell if you got the answer wrong. It can show you, hey, here's an example to show you that maybe if you got it wrong, why you were wrong. Sure. There's nothing wrong with, I mean, these concepts are these conceptual concepts. I mean, once you have an example to help, I mean, if you think of an example or supporting examples, the concepts become more intuitive and they're less conceptual. And that should make you feel more comfortable. Are there any questions on this example? Okay, great. I will stop the recording.